So this is Lab 13, and we're going to be talking about ridge regression in this lab. And this is associated with lecture 13, also on ridge regression. And we're going to be working with this TED Talks data set, which we had worked with last time. So I'm just going to read in my TED Talks data set. And if you remember, this data set had well, let's first look at the dimension of it, right? So it had about 2,500 TED Talks, about 400 variables. And if we look at, again, the variables has a bunch of variables on TED Talks, including a bunch of word frequency variables. And in particular, it had this variables views. And what we were interested in last time is predicting the views from those, the word frequencies and descriptions. So we can grab off, I'm going to grab off first just those variables that contain the word frequencies. So I'm just going to search through the column names for word, grab off those, and I'm going to subset that. So this TDM matrix has just my word frequency thing, variables. And then I'm just going to make a data frame that includes views, the views variables, what we want to predict, which is TED views and these word frequencies. And so if I do this, this is the kind of data I get my word frequencies, and I get my views that I want to predict. And it seemed last time that if I try to build a model with this, so maybe I want to predict log of views, and I want to predict that from all those word frequencies. My data is DF. So I can build this regression model. Seems reasonable to try and fit the regression here. And I can get my estimates of my betas, the coefficients of this model. And unfortunately, if I look at my beta hats, we'll see if I gotta scroll down eventually, I'm gonna get a bunch of missing values here, a bunch of NAs. Maybe not a bunch, but NAs every once in a while. I mean, last time we had kind of subset the rows, but we don't even need to do that in this case. If I look at how many of these betas are not finite, 21 of them apparently give me NA. And the reason for this is because if I look at this covariate matrix, my word frequencies, I can look at the rank of this thing, and it has a rank of 412, but my covariate matrix has 433 columns. So this thing is rank deficient. Another way of looking at this is if I look at the SVD of this thing, and I pull off those diagonal elements, there will be a lot of them. But if I scroll down here to the bottom, eventually I get a bunch of zeros. And that is telling me the same thing. It's rank deficient. So I can just look at the tail of those things. Those are kind of two quickest ways. Of course, the SVD takes a second to compute. Or I can use my favorite kappa. And I can get the condition number of X transpose X. So X transpose by X. And I probably want to make this thing a matrix. Otherwise, it's going to cause an issue. Let's try it like this. Is this going to work? Yep. And you see it's ginormous. It doesn't quite say it's infinite in this case, but it should be. But yeah, so basically I'm going to have, and it's funny that that is not infinite. I guess this is just an estimate of the condition number, because you look and you see these zeros here. Right, we made this claim. If I look at X transpose X, right, if I look at, let's say, the eigenvalues of x transpose x, again, eventually I'm going to get zeros at the end here. And so this shows me that this thing is rank deficient. Or I could look at the SVD of it, but what I had claimed is that kappa is the minimum, or is the maximum over the minimum, right? So that's probably how this is actually computing kappa. You want to see if this is how it's actually computing kappa? My claim was this is the max over the min, right? Oh, don't want to rename kappa. Let's just calculate this. And indeed, it's actually going to, so my minimum eigenvalue for x transpose x is actually slightly negative. It's really 0. But so in any case, it's a big number here. Let's just do it like this. Go. Big number. So this thing is very poorly conditioned, and that's why we're getting NAs when we try to fit this. And so our approach to solving this is to use ridge regression. And so let's say ridge regression is our solution. And so we can do that with the packages GLM net, which is, I believe, the same one we use to fit logistic regression. Is this not stalled? Install? Well, let's install that real quick. And I should be able to load it. There we go. Okay. And GLM net is going to have a function to fit a ridge regression. And the function, and we'll talk about next time why it's named this. GLM stands for generalized linear model, which we kind of talked about a little bit. We talked about logistic regression. And GLM net doesn't have the greatest interface, but let's actually just look at this function. It's not going to be the most useful help page. It says fit a GLM with lasso or elastic net regularization. After next lecture, this will make more sense about what lasso and elastic net are, but we can fit it using, we can fit a ridge regression using this. Elastic net is a more general term, so if we set certain parameters this to be correct, this alpha parameter, we're going to be able to use it if we set it correctly to fit a ridge regression. But its arguments are x and y. I don't believe it has a kind of formula interface like the standard regression, so we're going to need to pull out the x and the y variables. There are packages in R that will give it the kind of standard, formula interface, but I don't believe that it has a formula. Oh boy, there's a lot of help here. A formula interface for this. So we need our x matrix, which actually we already created, right? There's x, and y was this views, right? So if I want to get my ridge fit, I pass it in x, which is my capital matrix x, and y, which is what I call little y. I have to specify the family because we're doing just kind of least squares regression. We're not doing anything fancy like a logistic regression. We say Gaussian. We want to do a logistic regression. You would say binomial, right? And then the fit ridge regression, we have to specify this parameter alpha as 0. And we'll talk about next time what that parameter does, but just suffice it to say, setting it, GLM net fits a wider class of models, and to have it fit a ridge regression, we have to set alpha to be 0. So we call this, and it actually is pretty quick to fit the ridge regression. And so if I just print it out, it tells me my call, and it gives me some information. So it doesn't have as useful information, but one thing we want to get, of course, for our models, we want to get the betas, right? So if I do fit.ridge beta, this should give me my betas, and you see all these betas, all these rows associated with my variables, but then you see a bunch of columns. So what's going on here? So if I ask for dimension, this is 433 by 100. So what's going on here? What's happening is that if you remember, Ridge has a parameter lambda, and you have to specify that parameter. And I didn't specify that parameter when I called the fit function to fit Ridge. I didn't specify lambda. And so it's actually just choosing a sequence of lambda values through its own internal machinations and fitting using all those different lambda values. And it chooses as by default 100 different values, and it's giving me the betas for all 100 different values of lambda. This is useful ultimately because we have to tune this parameter lambda. We'll do that through a cross-validated thing at the end of this lab. But so by default, it's going to fit using a whole bunch of different lambdas. And we can specify the lambdas directly, and we'll see how to do that. But so that's what this is giving us. It's giving us the 433 variables, right? Remember, x is 433 variables, and this beta matrix is going to have 433 rows for different variables and 100 for different values of lambda and trisam. One of the nice things about this is it allows us to kind of plot what's going on with Ridge really nicely, kind of right out of the bat. So one thing we could do is we could plot, for example, the betas against the lambdas. So in fact, we're going to look at the log scale of the lambdas because they tend to be pretty big. And we're going to plot against the betas. We're going to make this a line plot, tight as hell. So my x label is log lambda, and my y label is the value for my betas. So let's plot this. So when I do it, this is what I get. So again, my x-axis is on the log scale, the penalization parameter, that constraint on the betas, and on my y-axis is the beta. And I have a different one line for each of my 400 covariates here. And as you can see, as I increase lambda, I penalize my fit more, I constrain my fit more, and what happens is it's pushing all my betas to 0. And if I push this out large enough, eventually all of my betas are just going to 0 out. If I don't penalize at all, so I have a very small or relatively small lambda, then I'm going to get very different covariates, and I'm going to not have things pushed to 0. And as I push it towards 0, as I push lambda large, everything gets pushed towards 0. Now we could directly specify the lambdas. If I go back to my Ridge regression fit, which was somewhere around here, this was it. I could explicitly say specify a sequence of lambdas. So I don't know what's our favorite sequence. Let's do powers of 10. So we'll do 10 to the 10 to the different powers. So this is a huge sequence. How long is this thing? 500. Okay. And so if I just do, so It's going to start at 10 to the 5th and end at 10 to the 10th. So it's quite large values of lambda. And I could do my fit, and I could say lambda is, and I can actually pass in a whole sequence of lambdas to test. And it will try all of them. Doesn't take too long to fit. And I could again do my plotting here, for example. I could plot these over what I chose. Looks kind of similar. What's a different sequence? Let's just specify the length as, I don't know, let's just do 100. And there's a sequence. It's an even wider sequence. So you can see as I get to very low values of lambda, I don't do any penalization. And it's not until I get to these higher values that it then kind of squishes everything to 0. So tuning this lambda parameter is quite an important thing to do. And there's actually a built-in function in this GLM net package called cv.glm net, and it has a kind of very similar interface to the normal call just to do the fitting. It's called cv.glm net, and you pass it in basically the same stuff as you would the normal fit. You have to specify this lambda sequence, and it's going to give you cross-validated errors for the different values of lambda, and it's going to allow us to choose the best value of lambda here. So again, pretty fast, and I can just straight up plot it. And when I do, I get a plot that looks something like this. And you can see that it looks about somewhere around 10 to the 15. So this is a real nice plot. This is the MSE against log lambda. About 10 to 15, that's minimizing my cross-validated MSE. Although I have really big error bars here. Now I realize now we actually wanted to do this all predicting log of the views. So maybe we go back and redo these using our log of the views. I think log views is going to give us a better prediction. Let's see. Yeah. Oops. So I really want to do log views. Let's see what this does. Ooh, that's much different. Doesn't really matter for the sake of this, but just for the sake of doing good modeling. Let's see what happens. Ooh, so as you can see, if you change different, if you change either your y or you change your x's, you're going to get different, kind of different behavior. So this lambda sequence probably isn't the correct sequence because we're not really finding a minimum here. Let's change our sequence. Let's say -10. Let's do a huge wide sequence. Okay. Let's do a cross-validated fit. That's giving us some errors. That's all right. Okay, so now we get something now predicting our log views that looks more reasonable here. And you can actually get out the minimum value here. So cv.ridge lambda min will give me the value that minimizes, that it estimates as minimizing. So it's basically the minimizing value here. So that's cool. So that's kind of an inbuilt cross-validation. We don't really need to work too hard. And so we can form our final model, our best ridge model, which if we go back up and copy our code here, let's see, let's just call this one best ridge. And what's my lambda seek? I'm just going to have one lambda, which is this, cv.ridge lambda.min. And this would be your best model. So I could, for example, look at my betas, and these are going to be the estimated betas, and you can do prediction and other things like that. But that's kind of the basics of how you're going to form the model. And next time we'll look at this in a little more detail, along with some of the other stuff we look at. But I'll stop there.